we'll be looking at conditional distribution. We define two conditional distributions, the distribution of x given y and the distribution of y given x. All right, so the first one is the distribution of x given y. And then the second one is the distribution of y given x. It will help if you can relate the first and second distributions with your knowledge of probability. You remember that when there is independence, probability of A intersection B, which I have written this way on purpose, becomes this when there is independence. However, when there is no independence, that's when A and B are dependent in one way or the other, which means A may be dependent on B. B may be dependent on A, as in this case, or A may be dependent on B, as in this other case. So the two cases actually means there is dependence between A and B. All right. Now, looking at these two, let me call this 1, 2, and 3. So looking at the third one, I mean the second and third one, the second and third ones, you number 1, number 3, so the second and third cases, you find out that you can compare what you have in the second and third case, the second and third cases, with what you have here and here. Now you see that it's just a matter of changing the subject or formula. For instance, number 3 would become probability of A given B equal to the probability of A, comma B. And don't forget, we use intersection in place of comma actually when dealing with probability, but you can just to understand what we are doing in this case, you can actually leave it this way. All right, now, so what we have done here, so if you remember the concept of probability, then you can use that with your your conditional distribution. So in that case, you are going to have, so whatever is down here comes down. So just look at it, it's very simple. You have x up, y down. Okay, so f of x comma y. So which is the same thing, y, x. So you just put f of x comma y as the numerator in both cases. But in the first case, because y is down, y is the numerator. So f of x given y, you do f of y as the denominator because y is down. And the second case, because x is down, you put f of x as the denominator. All right, so that's the similarity between this and this. So it follows the same or a similar process. All right, but mind you, don't forget that we are dealing with a function here. It's a probability function anyway, but it's a function. All right, now we can go on. So we move on. Now we want to look at conditional probability. Conditional distribution, marginal distribution. We are looking at both of them, the conditional and marginal distribution when there is independence. Now, if you remember from your concept of probability, when there is independence, we said something about the fact that probability of A, probability of B will be equal to the probability of B given A, and the probability of A will be equal to the probability of A given B. And when that is the case, it means that you are going to have this as the resultant stuff. So it means that probability of A, comma B, probability of A intersection B actually will be the probability of A multiplied by the probability of B. All right. That being said, we can go back to our conditional and marginal distribution. Now it means that when there is independence, your conditional distribution will be the same thing as your marginal distribution. All right, so we we need to go back to what we actually termed a marginal distribution. Now, don't forget the marginal distribution is just the distribution of x. So that means when you take x alone, uh, um, that of y when you take y alone, and this was what we did. You remember that you. So now we have defined marginal distributions to be this in the case of discrete and continuous functions, and we are now saying that when there is independence, then you are going to have what we have above to be true. Now, the distribution of x given y will be the same thing as the distribution of x alone, and the distribution of y given x will be the same thing as the distribution of y alone. Now, the meaning of this is that when there is independence, it means that just forget about this side. Imagine that this side did not exist. So look at the equation from here to this side. So it means that when you multiply y with x, which is something like what I have here, all right. Now, that is what you are going to have when x and y are independent. So that's what we are trying to say here. And it's a very important thing to note. It means that when we start doing certain calculations, maybe you're given a particular f of x, comma y, and then you divide it by f of y, then you get f of x. Maybe you already had that before. You can immediately say, okay, wow, that means x and y are independent. All right, so we're going to see how that is important. I have taken time to write that of the probability of the intersection of A and B equals to probability of A multiplied by the probability of B. Don't forget, we used to have this like this. Instead, doing that, I did that so that it could make it easier for us to understand what we have here. All right, so we go on. Let's look at what happens to the variance and the mean of conditional distributions. You most likely have not forgotten the mean and variance in the case of your discrete distribution. Okay. So we defined the mean to be, maybe for instance, the mean of x now to be something like this. And then we went further to define the mean of, the variance of x now to be this. That's after obtaining the expected value of x squared. And then the variance of y, or rather the mean of y, was found to be something like what you have here. And then we went on to talk about the variance to be something like this after you have obtained this anyway. Now, then we obtain the covariance to be this one, what you see here. Okay, what you see here rather. So that means you need to obtain this, which is equal to this, the expected value of x, the expected value of xy. We had obtained expected value of x and expected value of y above. Now, I'm not concerned about this particular example, just trying to show you the formula because we are going to something a little bit different this time around. Now, let's look at the mean. Okay, all right. Okay, let's look at the mean and variance this time around. Now, when we have mean and variance, when we have a conditional distribution, the mean for the discrete case will become something like this. Now you see the difference here is just that the given y, x given y, so just the slash and then the y. So that's the difference, the slash and the y that is showing here, the slash and the x that is showing here. All right. So apart from the given y or given x thing that is showing, no other one, nothing is new actually. So if you, for instance, if you cancel this, you cancel all of this, you just have expected, okay, I mean summation of x multiplied by f of x. So that is if you cancel this one, actually, that's the expected value of x will be equal to the summation of x multiplied by e of x. What I'm saying is you have this. All right. So this is what I'm saying. But because you have given y, the given y has to reflect there now this time around. So that's what we are doing this time around. That's what we are showing. Now, but what do we mean by this? It means that we are going to have a particular value for y. That's what we are trying to say. So, for instance, expected value of x given y equal to, there are a range of values for y. Maybe you may, in the continuous case, for instance, it applies to the discrete case too, but let's do it this way. Okay, if for the continuous case, I mean for the discrete case, you have 0, 1, 2. So y will have to pick one of those values. So we may have something like y equal to, say, 0 here. All right. In the discrete case, um, it can take maybe, for instance, 0 less than x, or rather less than y less than maybe 2. Y can also pick any value from here. So that's what we are trying to talk about. So yes, so in the continuous case, you can have y falling between 0 and 2, and it could be anything. It could be 1.2, it could be 1, it could be 0. Don't forget that actually in the real sense, it could be 0, from 0 to 2. It could be 2 also. It could be 2, maybe 1.9, anything between 0, any number, any possible number in the continuous case. But in the discrete case, it can only be either 0, 1, or 2. All right, so that means you're going to be fixing that value here in place of this y. So you just have something like f of x given y equals to 0 or 1 or 2 or something. All right, so that's what our y will be representing as we continue. So there's supposed to be a y here. All right, it applies also for your x. In a similar manner, you can obtain the expected value of y given x equals to x, the variance of y given x equals to x, as well as this one, the expected value of y squared given x equal to x. So note that it's very important. So you could do that for this, and as such you can observe, you can obtain your variance. All right, so that's that about that. Please don't forget what you have as your formulas for all of them. So in the continuous case, you are integrating. In the discrete case, you are actually summing. So summing here, integrating here. The variance is always obtainable using the formula we have here. Once you have what you're looking for from here. So if you wanted to obtain the variance of y, that would be variance of y given x expected equal to expected value of y squared given x, right, minus the expected value of x given y, everything squared. Okay, now so that's going to be that of y. Now you know what we are looking for. Now you understand that it's now time for us to look at a small example. So let's look at that. Now, suppose that you are given a joint distribution, which is f of x comma y equals to, now, mind you, this question actually means that x plus y are together, so all over 12. So if you're to write that with a pen, you're going to have x plus y over 12. That's what I mean. All right. Now, so we can make that here. We are told to find or to show first that f of x comma y is a true probability function. Now, in order for it to be a true probability function, then what I have here must be equal to 1. I mean, when you do, it's a continuous distribution, right? You can see that from here. So we had previously stated that one of the properties of a bivariate distribution is that the summation over all the range of x and y should give us 1. So it's the same thing, the first and the second, number 1 and number 2 are the same. It's just that it's a matter of how you state it, but they're the same. Either way, we are saying that we should get 1. When we do a double summation or double integral over the range of the two variables that we are considering, in this case, x and y, and we are told that it should give 1. Whether it's continuous or it is discrete, it should give us 1. So our example is considering a situation, okay, considering a discrete, a continuous case. Now, so we use the double integral, and by doing that, over the range of x takes values from 1 to 3, don't forget that here, here, y takes values from 0 to 2, don't forget that here. All right, now, so when we do the integral, double integral, the first time we are doing the integration, our concern is y, because y is the inner one. So we'll take care of y first. And when we do that, we are going to get, just bring 1 over 12 outside. And when you do that, you're going to have xy plus y squared divided by 2. How? Take x. X is a constant, so y is your concern here. So since x is a constant, if you integrate a constant, you should get y as your variable of interest. So you multiply that y by x. The same thing happens, a similar thing happens to y. Y is our concern, so definitely you don't forget that integral of x is equal to, the integral of x will be equal to x raised to the power of n plus 1, or rather x raised, oh yes, let's do it. Integral of x raised to the power of n will be integral of x raised to the power of n plus 1 divided by n plus 1. Sorry, don't mind the way this looks. This actually means integral. All right, if you don't forget that, that's what I've done here. Since it was y plus 1 before, I mean y raised to the power of 1 before, I just added 1 and divided by 1 plus 1. All right, so that gave me what I'm looking for, and that way we are done. So, but then because we have range of values for y, that's 2 and 0, we substitute the values that we have here for y. So the first time we substitute 2. So 2 times x gives us 2x, and then we put 2 raised to the power of 2. It gives us 4. Actually, we had something like 2 raised to the power of 2 divided by 2 when we substituted 2 here. But then that will become 4 divided by 2, and that will give us 2. All right, so that is why we have 2 here. Don't forget that, please. And that way we continue. In the second case, whatever you substitute will give you 0. You put 0 in place of y, you get 0. 0 times x is 0. As 0 raised to the power of 2 divided by 2 is still 0. So 0 plus 0 is still 0. That's why we have what we have here. Now we go on to finish that, and then we get 2x plus 2. So now we want to integrate with respect to x. So from here, something is missing. I'm going to put that Okay. Now we have something missing, so let me just put that with the red. You can follow up. The x actually supposed to come in before the equal to 1. Now we are integrating this with respect to x. When we do that, we are going to have 2x squared over 2 plus 2x, and then we get to fix the limits that we had, 1 and 3, and then by fixing the limits and doing all the maths there, you get 9 plus 6 minus 1 plus 2, that becomes 15 minus 3, then you get a 12, and then you divide and you get 1. So that means that what we have is a true probability function. So we've proven that what we have been given, the f of x, which is equal to x plus y divided by 12, which I meant to be this, is actually a true probability function. So the second question says find the conditional distribution of x given y, then you find its mean, and then finally its variance. Now, but we're given a condition when y is equal to, well, I don't think that was the case anyway. I think the case was when y is equal to 1. All right, so we can go on. Now, yes. Now, we are considering a situation where we have the distribution of x given y. Don't forget that distribution of x, sorry, the distribution of x given y, and we want to go on to obtain that. Now, if we're going to, that means the distribution of x given y, it's going to be what we have on the board, the formula there. And since we know that, we just substitute the values. We know that of f of y, we know that of f of x given y. And then by doing the substitution, using the formula, don't forget the formula here, we will get, so fixing everything that we have, f of x given y will be this, and then f of y will be this. And that way we can divide, and by doing our division, we eventually get x plus y divided by 6y, and the range coming from here still remains. All right. Now, but we were told that we should look for the conditional expectation of x given y equal to 1. Given y equal to 1, the conditional expectation of x given y equal to 1. And that's what we want to do now. So in order to do that, we know that the expected value of x given y is this, but we know that if it is for y equal to 1, it becomes this. All right, now we now substitute 1 any place, and in any place where we find y, don't forget y is here and y is here. So because y is here and y is here, we put 1 in the places where we find y. And then when we do that, we get x plus 1. So now, actually, there's supposed to be an expected value of y equal to 1 here. So before you have the bracket. All right. Now, it will be equal to 1 over 6. We're bringing 1 over 6 out. And then x multiplying x squared plus 1 becomes this. And then we go on, substitute. Okay, we integrate. When we do the integral, we are going to get x raised to the power of 3 over 3 for this one, and then x raised to the power of 2 divided by 2 for the second one. So we fix in the values 3, and then in this side 3, in this side 1. So 3 here in the first side and 1 in the first side. So accordingly, we are going to get all of those mathematics that you do, and at the end of the day, you get 76 divided by 36. All right, so you can follow up from there. The other things involved here are just mathematical calculation. So you had 3, this is x raised to the power of 3, divided by 3. So in the first case, in this bracket here, you are putting 3 in place of x. So wherever you find, like here now, you put 3 there. Here, you put 3 there. All right, so, and raised to the power that the x was raised to. So x is raised to the power of 3 here. X is raised to the power of 2 here. So, and so that's that. Now, in the second place, you also put x. What is the value of x now? 1. It's going to take 1. So, this should be 3 actually. 1 raised to the power of 3. That's this now. Then 1, you put 1 in place of x, 1 raised to the power of 2. And that gives you what you're looking for. So the calculation, the LCM, everything, at the end of the day, when you finish, you are not going to get, for the first bracket, you get this 18 plus 9 over 2. That gives you 27 over 2. The second bracket, you get 2 plus 3 divided by 6. That will give you 5 over 6. Now, when you do the LCM of the 2 again, you get this, and then you do your computation. You get 81 minus 5 divided by 6. And at the end of the day, you get 76 divided by 36. That gives you 19 over 9. All right, so that takes care of the first one. Now, coming to the second one, you have the expected value of x squared. Okay, we are still doing, we are trying to find the variance now. We found the mean for the function that we called the marginal distribution of x given y. All right, now we are now looking for the expected value of x squared given y, and that will be equal to this. So in the case where y is equal to 1, expected value of x squared given y equals to 1 will be what we have on the board. Don't forget that the difference between this and this is actually the fact. I mean, the difference between this and this is just y equal to 1, actually, equal to 1. So don't forget about that. It's the same thing. This is more general, like y could be anything. And if we wanted to make it more obvious, we just put y equal to y in addition. So, but even if you write it this way, you're not wrong. But it's more explicit this way. All right. Now going up or continuing the stuff. Now we look at this. In this case, we're using x squared here, multiplied by x plus 1. Don't forget that this x plus 1 over 6 is coming from our conditional distribution above. The conditional distribution when y is equal to 1. So this is what I'm talking about. This, and which is equal to this. All right. Now, knowing that we are now multiplying this by x squared, the x squared is coming from here. Don't forget how the expected value of x squared is obtained. X squared is multiplying f of x given y equal to 1. And by doing that, we bring 1 over 6 outside. So that will give us 1 over 6 multiplied by x cubed plus x squared. Now, by integrating, we're going to get x raised to the power of 4 plus x raised to the power of 3. I mean, x raised to the power of 4 divided by 4 plus x raised to the power of 3 divided by 3. Then, when you substitute the limits, 3 and 1, you end up getting 3 raised to the power of 4, then divided by 4, 3 raised to the power of 3 divided by 3. So that's the first time when x is 3. And then when x is 1, you end up getting 1 raised to the power of 4, then 1 raised to the power of 3. All right, so divided, in the first case you are divided by 4, second case you are divided by 3, and then you go on. Now looking at 12 as the 12 as the denominator here, I mean the LCM for this, so you make it the denominator, and by making it the denominator, you can divide 12 by 4, you get 3 multiplied by 3 raised to the power of 4. 12 divided by 4, you get 12 divided by 3, rather 12 divided by this 3, you get 4. and then 4 multiplied by 3 raised to the power of 3. All right, then you go on. The LCM is 12. 12 divided by 4 is 3 multiplying 1 raised to the power of 4. The LCM is 12. You divide by 3, you get 4. The 4 here. Then you multiply by this 1 raised to the power of 3. And then when you have done that, it becomes 1 divided by 6 multiplied by 351 divided by 12 minus 7 over 12. All right, so having got that, this one is what resulted, everything here in bracket is what became this. Everything here is what became this. Okay, so having got that, now you can now do your subtraction. They have the same denominator, so it becomes 351 minus 7 over 12, and that becomes 344 divided by 72. 6 multiplies 12 to give you 72. So it multiplies 12 to give you 72, and then you, by reducing these two, you get 43 over 9 as your answer. Now, going on, we can now find the variance. Don't forget, we obtained the expected value of x given y equal to 1. This in bracket to be 19 over 9. You may return back to see that. Okay, so this is expected value of x given y, and actually expected value of x given y equal to 1 is what we have here. It's equal to 19 over 9. All right, now in that case, okay, we return back to obtain our variance. The variance now is equal to 43, okay, divided by 9, which we obtained to be the expected value of x squared. This is here, x squared given y equals to 1. All right, and that's by substituting everything that we have now. We are going to get 43 over 9 minus 19 divided by 9, which is about 2. When you do your mathematics, you get 361. For this particular one here, you get 361 divided by 81. And then when you find the LCM and then you do your mathematics, you end up getting 26 divided by 81 as your answer. All right, so we are done with the second question, and we are left with one more question. So we've obtained the conditional distribution for x given y equal to 1, and we have obtained its mean and its variance. But the next question is, how can we find the conditional distribution of y given x, its mean and its variance also? That's also easy. We will do something very similar to what we have done before. Of course, I said similar, but not, okay, we follow a similar step, let me say that way, but we are not going to have the same distribution. So now this is going to be what we will have. We are looking for the conditional distribution of y given x. Now that becomes this, and since we know the distribution of x to be, don't forget, let's return and find the distribution of x from the question. Okay, we were not actually given. I didn't write that before. Please note something, and in addition to what we have as the question here, the distribution of x alone is actually equal to okay, the distribution of y. Please, in case you were confused while I was solving that, where did this man get this from? Okay, I'm sorry, I didn't write that earlier. Actually, y itself is equal to y over 2. That's part of the question, please. Take note of that. It's part of the question. It should have been written. 0 is less than y. Sorry. 0 is less than y is less than 2. So note that the range of y here must be the same thing as the range of y here in your question. Now, that of x should be 3 over 20, is it 26 now? 26, 3 over 26 multiplied by x squared, and then 1 is less than x is less than 3. Now this is our question actually. I'm supposed to have given these ones before now. So I'm sorry about that it didn't reflect or it wasn't showing there. Now, so alongside what you have been given here, you're supposed to have this one also. That so given a joint distribution, show that f of x comma y is a true probability function. Now, we will now need to find the conditional distribution of x given y and y given x, given what I have here. So the question actually is complete when you have this. All right, so this is what we should have been given, all of this. Now, so please note that's part of the question. Now, going back to what we're doing. So we were to look for the conditional distribution of y given x, and x itself, I've written it above, is supposed to be, I've done this actually. So f of x, I mean to say, is actually 3 raised to the power of x squared over 26. All right, don't forget the range. 1 is less than x is less than 3. Okay, and we already know f of x given y. All right, so you're supposed to spell this out, and I've just spelled it out. So by doing the division, you are going to get this, and then at the end of the day, you have 13 multiplied by x plus y divided by 18x squared. Now, the reason why you're seeing this range is because we have a range for y, we also have a range for x, and both x and y are showing here. All right, so this is the general distribution, but we were actually told to find the distribution of y given x equal to 3. So don't forget, let's go back to the question and see that. So find the distribution, the conditional distribution of y given x, okay, now, given x, its mean and variance when x is equal to 3. So we are going to do that. We've obtained the conditional distribution, but we need to obtain it, I mean the mean and variance when x is equal to 3. So when x is equal to 3. So we are going to do that now. And going back, returning to where we came from. Now, x equal to 3 implies, this is plus please, x equals to 3 implies that we are going to put 3 anywhere we find x. So if we find x here, we find x here, we'll put 3, that will be 3 squared. We find x here, so we'll put 3 there. That's why you have 3 plus y. All right, so going on, you're not going to have 18 times 9, and that should give you 162. So you have 18 times 9, that should give you 162. And that way we already have the conditional distribution of x given, y given x equals to 3. So, but the conditional distribution of y given x is this. So that's the general one. Now, but specifically, when x is equals to 3, conditioned on the fact that x is equals to 3, we are going to have this one. Now, continuing, we want to obtain the mean Now, in order to obtain the mean, we integrate over the range of y because we are looking for this. Don't forget, expected value of y. So we integrate over the range of y. The other time when we're looking for the expected value of x given y, we integrated over the range of x, not the range of y, because x is what we are concerned about. Now, in case you really want to confirm that, you want to verify, you can see that here, it's the same thing when you're looking at the expected value of x squared anyway, or rather it's similar. You integrate over the range of, so x here, don't forget that. Now, so going back to where we came from. All right, now we are going to have all right, y to multiply this. Please, there's supposed to be a y here. Y multiplied by f of y giving x equals to 3, and that y is what is here. F of y given that x is equal to 3 is this. So we just put that here in the box, and then multiply, and then we have, sorry, there's a y here, don't forget that. Then we have, when we open the bracket, we end up having, okay, 3, when we multiply y with this, we end up having 3y plus y squared, so we bring 13 to be with 162, and then we take them out. Then we are going to have this. Then we integrate, and when you do that, you are going to have what we have here, 3 multiplied by y squared divided by 2, y raised to the power of 3 divided by 3, and the limit 2 and 0. Then we go on, and when we do, okay, the LCM of 2 and 3 will be 6. Then you divide 6 by 3, you are going to get, 6 by 2, the 2 here, divide 6, you're going to get 3 multiplied by this 3y raised to the power of 2, that's why you have this here. And then you go on, 3 divide 6, you get 2. And then when you bring that 2 here, you multiply it by y raised to the power of 3. That's how you get this. And that way we continue doing your mathematics. You are going to get 9 from here, 9 times y raised to the power of 2, and then from here 2 times y raised to the power of 3. And then when you continue, you end up getting, okay, we bring 1 over 6 outside, and then we have this, so 1 over 6 is outside, and then we can just substitute 2. So in the first case, when we substitute 2 in place of y, we have this. So when we put 0 in place of y, we are going to have this. And when we do our mathematics, so 2 raised to the power of 2 is 4 multiplied by 9 is 36. 2 raised to the power of 3 is 8 multiplied by 2 is 16. 9 times 0 is 0. 2 times 0 is 0. 0 raised to the power of 2 is already 0. You should know that, I believe. 0 raised to the power of 3 is 0. All right, now it now goes on to be, okay, 13 divided by 972 multiplied by 52. And that becomes 676 divided by 972, and that will be, so when you reduce 169 divided by 243, and if you like, you can put it in decimal form, but I prefer to leave it in fraction form because of what you are going to see very soon. You tend to be more accurate when you have more decimal place, but this is going to be 4, so your answer may tend to shift somewhat, but it depends on you. You may like it that way, but I prefer to use the fraction. So, but if you like the decimal, fine. All right, so we go on. We obtain the expected value of y squared divided by x equal to 1. Just be sure that your approximation is correct. That's another thing. If it is, there's no problem. It may just be 0.1 or maybe 0.00 something difference, just a small difference. You may end up having 0.69, maybe 5, 6, right, or 5, 4, which is, depending on the case, it may be negligible, but make sure your approximation is correct, so that that's just it anyway. But in order to prevent that, it's always preferable to leave it in fraction form if possible. Now, the expected value of y squared divided by x equal to 1. Now, in order to get this, don't forget that because we have y squared here, y squared shows here. And then multiplying what we had obtained before, now we get all of these, and then we do the normal stuff. This goes outside, and then y squared comes in to multiply. Then you get 3y squared plus y cubed. And then when you continue, you integrate this, it becomes this, what you have there, 3y cubed divided by 3 plus y raised to the power of 4 divided by 4. And then this will cancel this. So you are going to have y cubed plus y raised to the power of 4 divided by 4. Now by we identified the LCM to be 4 in this case. So this is over 1. 1 divided 4 becomes 4, multiplied by y, 3, that gives you that. And this one, 4 here is 1, 1 multiplied by y raised to the power of 4, you get this. Now we bring 1 over 4 out, multiply this, that becomes 13 divided by 648. And then we go on to substitute, to put the values of the limits here, now 2 and 0. So we'll put 2 here. And when we put 2 here, we are going to have this. So 2 raised to the power of 3 becomes 2 raised to the power, y raised to the power of 3 becomes 2 raised to the power of 3 here. Y raised to the power of 4 becomes 2 raised to the power of 4 here. So in a similar way, when we put 0, we have this. So the case where y is 2 and the case where y is 0. All right. Now, when we go on, this will give us 0 definitely. So we have minus 0 here. And then this will give us, this first one, 32. This one will become 32. This will become 16. And when we have done that, we multiply. We are going to get 624 divided by 648. And you can reduce it to become 26 over 27. And now we want to obtain the variance. And in order to get the variance, we need the expected value of x, the expected value of y squared, given x equals to 3. Now we have obtained this to be 26 over 27. And then we need the expected value of y, given x is equal to 3, which we obtained earlier on to be 1 over 69 divided by 243 here. Okay, so we said, therefore, expected value is supposed to do that anyway, or we are supposed to do that anyway. Y squared, y, not y squared this time around, equal to this. So, you see that from here. So, and it's not just y squared, it's actually the expected value of y. Not just, okay, so don't forget, we obtained this earlier on, and its value is this, 169 divided by 243. All right, so going on, we are fixing those values now in their respective places, and then we get this. After squaring, we obtain this. So when we square 243, we also obtain this. Now we square 169, get this. Square 243, you get this. Now, doing your LCM, you find out that 27 can actually divide what you have here. And so the LCM of the two of them is 59,049. And then you divide 59,049 by 27, you get 2,187. You multiply by 26. Okay, that gives you 56,862. Now you divide this by this, that's 59,049, you get 1. So that one multiplies this one to get this one. All right, now so you get 28,561 there. Now, when you remove 28,561 from 56,862 and you divide by 59,049, you are going to get 28,301 divided by 59,049, and that will give you 0.4793. So actually, as I've been saying, it's optional. You don't have to express it as a, it depends on you anyway, if you want it to be in decimal form. So you could stop here, you're still correct. All right, so that's that about that. And with that, we are actually done with the question. So we have obtained all that all that was demanded of us in the question. So we were told to obtain the conditional distribution of x given y, its mean and its variance when y is equal to 0, and then also the conditional distribution of y given x, its mean and its variance when x is equal to 3, and we've done all of that. So that leaves us with one more thing, and that will be the case where the conditional distribution is equal to the marginal distribution, and that happens when you have independence. So conditional distribution equal to marginal distribution when there is independence between your variables, which may be x and y. Also conditional distribution equal to marginal distribution. Now, let's take an example on that. Given that f of x equal to 1 over 4 1 over 4 multiplied by xy, for the range x is between 0 and 2, y is between 0 and 2. Now, in this case, then we will have f of x given y to be 1 over 4, don't forget from here, 1 over 4 xy divided by, we are dividing by f of y, that will be f of y from here, this, and that will be what we have on the board. Then it will result to 1 over 2x. Mind you, x is not in the denominator. What I've written here is 1 over 2 multiplied by x. Okay, or you just have it as x over 2, the same thing. All right. Now, hence, f of x given y is the same thing as f of x. Look at that again. From our question, f of x is 1 over 2 multiplied by x, and f of xy that we just obtained is also 1 over 2 multiplied by x. And don't forget, the range of x is from 0 to 2. That's the same thing here. It's between 0 and 2. And now look at that, please. You find out that y is no longer here, so exactly equal. These two are equal. And that's that about the first one. So the second one, we have, all right, f of x comma y divided by f of x now. So we are looking for the conditional distribution of y given x. And when we substitute again, don't forget f of x is 1 over 2 multiplied by x. So we substitute that here, and then we get 1 over 2 multiplied by y. Y is, okay, half is a constant coming before the variable y. Now, and that's for the range. Don't forget 0 less than y less than 2. Now, again, the conditional distribution of y given x is the same thing as that of y. Look at that of y up here. We have it to be 1 over 2y with this range, and that's what we have here again. But what we obtained is this. So meaning that the conditional distribution of y given x is the same thing as the marginal distribution of y. All right. Now, in this case, we have just shown that when there is independence, then the marginal and conditional distributions are the same. You will notice that we actually obtain f of x comma y by multiplying f of x and f of y. And that will be obtained by saying 1 over 2. So f of x is 1 over 2x. Then when you multiply that with f of y, which is 1 over 2y, you are going to get 1 over 4 xy. All right, so that's how we obtained the joint distribution for x and y. The only thing we just need to do is, considering what we were given, because we have a joint distribution, now we just have to say, comma, 0 is less than x is less than 2. That's the range for x now, the range of values for x, and then 0 is less than y is less than 2. That will be the range of values for y. So you find out that by multiplying the two distributions, we actually obtained our joint distribution. So it means that they are independent. So if you are given a distribution and you are asked, show that the distribution, whatever it is that is written here, anything it is, maybe for instance, this is not, I'm not saying now that this is a distribution, but let's just assume that this is it. Okay, and you have some values, some range of values for x and y, and then you are asked to find or to show that to show that they are independent. Then what you'll be trying to do, maybe you have this now, and then you are told that where f of x equal to something and f of y equals to another thing, given the range and everything, then you are asked to show if that, or to determine if they are dependent, or to determine if they are independent. Let's take a case where they are independent, for instance. It doesn't matter how the question is asked. What matters is that you will need to come and look for f of x given y, or you could go straight away by saying, okay, let's check. If they say show whether or not these two are independent, then you just need to do f of x comma y to be equal to f of x multiplied by f of y. So you tell us that if they are independent, then this, what I've written here, should be true. So when you have told us that, then you go on to find f of x. So you substitute the stuffs you are given. Where you have f of x, you put it here. Where you have f of y, you put it also, and then you multiply whatever you have there. So let's assume you have something from the first one multiplied by something from the second one. Whatever you get, you now check, is it equal to what you have from the original? Now, in the case where we were given f of x to be maybe 2x, and f of y to be maybe y, 1 over y, then doing the 2, multiplying f of x by f of y will give us 2x multiplied by 1 over y, and that should give us 2x over y. So don't forget, I'm not writing the range of x and y in this case, but you need to specify the range of x and y as we did here. You need to. All right. Now, if at the end of the day, what you have obtained is equal to, you may label this, for instance, equation 1. So you say f of x, y, maybe you label this equation 2, in 1 equal to f of x, x comma y in 2. So if you write that way, you say, therefore, they are, x and y are independent. That has shown that they are independent. But in a situation where they are dependent, then you will not have our f of x comma y in equation 2 to be equal to our f of x comma y in equation 1. So you need to be mindful of that. So we have just shown that when the marginal distribution for x, this is marginal, and this is conditional. So when the marginal distribution for x and the conditional distribution for x are the same, and when the marginal distribution for y and the conditional distribution for y are the same, then we have independence. So that's what we are talking about. It means that the independence brings the marginal, okay, does not put any distinction between the marginal and the conditional distributions. So don't forget that. And with that, we have come to the end of this lesson. Thank you.